Heavy fermions. I'm going to assume you all know what the word heavy means, and start with a quick clarification of the term fermion. Fermions are particles which can't exist in the same state at the same time, i.e. they follow the Pauli exclusion principle. This includes particles such as electrons and protons. They are governed by Fermi-Dirac statistics, which is where the name comes from, and they're often contrasted with bosons like photons, which obey Einstein-Bose statistics. The physical distinction between a fermion and a boson is the particle's spin. Bosons will have an integer value of spin, while fermions have half-integer values. As useful as it may be to understand the specific distinction between fermions and bosons, really, we mostly care about electrons. In a material, electrons occupy energy states, and since these states can't overlap, we assume that statistically, all of the lowest energy states will be occupied. This effectively buries most of the electrons in a material, since small fluctuations in energy can only change their state to a slightly higher position, which is likely already occupied. However, in a conductor, the electrons near the surface of these occupied states, referred to as the Fermi surface, are able to move around in physical space, allowing for electrical conduction. Now there are many complicated interactions to account for here, so these electrons at the Fermi surface are often modelled as a Fermi liquid. The idea here is actually somewhat simple. While many interactions can occur between fermions and with their surroundings, we can often model the end result as if the fermions actually weren't interacting with each other at all. This will obviously produce some odd results, but tweaking a few numbers here and there, theoretically changing the physical properties of our particles, will leave us with an accurate model. And so heavy fermion materials have several complicated electron interactions, but in many ways the end result matches with a much simpler model, in which electrons don't interact, but are heavier than normal. I'm Barry, representing Group I, and I'm going to be talking at you about heavy fermions for the next 12 minutes. A conductor, in some models, is composed of a lattice of ion cores and a sea of delocalized electrons. In a standard conductor, the electrical resistance is dependent on the conductor's temperature. A higher temperature means that ion cores vibrate more, disrupting the flow of electrons, scattering electrons from their paths. This means that as the temperature is reduced, the resistance drops. At low temperatures, the resistance is mostly caused by impurities and defects in the conductor, meaning we expect the resistance to reach a minimum at 0 Kelvin. You may think that at low temperatures, electrons would still scatter just by random collisions with the stationary ions. But the resistance of most metals falls far too low for this to be the case. Instead, we theorize that the paths taken by the electrons are characterized by what is called a block wave, which simply avoids the ions entirely. This means that at higher temperatures, the ions can still vibrate into the electrons' paths, but also means that at low temperatures, it is possible to reach very low resistances too. Now, I'm sure you all know about superconductors, wherein at some critical temperature, the resistance drops to 0. As interesting as that may be, we're discussing the handful of cases in which, below a certain temperature, the resistance begins to climb again. This occurs when defects within the conductor are magnetic, which is to say the defects have non-zero spin. These magnetic ions have free, localized magnetic moments, which act normally at higher temperatures. However, at low temperatures, the ions are screened by electrons. Due to its spin, the ion has a quantum tunneling interaction with electrons, in which an upspin electron within the ion may be swapped with a downspin electron in the delocalized sea. This can occur repeatedly, swapping the overall spin of the ion from up to down and back again, so frequently that the ion appears, on average, to have no spin at all. This is referred to as the Kondo effect. This interaction scatters the electrons being released, effectively increasing the resistance of the conductor. For one-off impurities placed randomly, this effect builds up the resistance of the conductor as the temperature falls. In an alloy containing many magnetic ions throughout the conductor, arranged in a repeating Kondo lattice, the resistivity can once again begin to fall as the scattering begins to conserve electron momentum. Each scattering begins to feed into the next, in a manner very similar to Bloch waves, meaning the resistance of the conductor can drop as lower temperatures help to stabilize the lattice. This drop, when graphed, can therefore look very similar to the drop we see at higher temperatures, acting as though the electrons in these materials are heavier, but otherwise the same as electrons in normal conductors. Materials containing this Kondo lattice can therefore be considered heavy fermion materials. You may have noticed that there have been a few references to Jun Kondo. The Kondo effect, Kondo lattice, the Kondo problem. Oh, wait, no. We hadn't mentioned the Kondo problem yet. That'll come up in a bit. Jun Kondo is a Japanese scientist responsible for the equation which first began to explain the increase in resistance as temperature fell. It was him that showed the relation was a result of magnetic impurities in a metal. The Kondo problem arose from an weensy little impossibility in his equation. According to Kondo's calculations, if you reduce the temperature of a metal down to 0, the magnetic impurities could cause the resistance to become infinite. And while absolute 0 is theoretically possible, infinite resistance is not. In fact, each metal in which the resistance increase was observed had a temperature below which Kondo's equation would no longer apply. This temperature was named, you guessed it, the Kondo temperature. The Kondo effect was devised to solve the Kondo problem by Kenneth Wilson in 1975, and is responsible for yet more Kondo-inspired terms, such as the Kondo singlet, a quantum state occupied by the impurities and nearby electrons, and the Kondo resonance, a term referring to an energy around which many electrons occupied very similar energy states within the conductor. Apparently, Jun Kondo was something of a badass and everyone wanted to name things after him. The Kondo effect produces screened ions which appear to lack spin, allowing the impurities to act without any magnetic order, or paramagnetically. This is contrasted with the competing Rudderman-Kittel-Kasuya-Yoshida interaction, or the RKKY interaction. This interaction is caused by conduction electrons moving between impurities before they've been screened. Because of this interaction between neighbouring magnetic impurities, their spins can be ordered either ferromagnetically or antiferromagnetically. This magnetic order is at odds with the screened impurities, whose magnetic spin could point in any direction, and so the RKKY interaction prevents the Kondo effect from taking place. Simply speaking, this explains why certain metals, which might be expected to act as heavy fermion materials, might not. Whether or not the magnetic order of the RKKY interaction, or the disordered paramagnetism created by the Kondo effect, is favoured, can be associated with one constant, the hybridization constant, J. This is a constant used in the Anderson impurity model, which was the basis on which Kenneth Wilson solved the Kondo problem. But really, it has its origin in chemistry, not physics. When we look at atoms in isolation, electrons have what is considered to be a default arrangement. Within a compound, or in this case a repeating crystal lattice, this default arrangement can be bent into a more geometrically practical shape. This is called hybridization, and keeping track of it is mostly a matter of noting the resultant change in energy, which in this case can all be boiled down into one hybridization constant, sometimes referred to as the spin exchange coupling constant. Its exact value can vary between materials as a result of their chemical makeup, but it can also be precision controlled through the pressure exerted on the material, or by placing the material in a controlled magnetic field. By examining the phases observed as the value of J is increased, we can see that small values of J favour a magnetic order, while larger values favour the heavy fermion arrangement. At the border between these regions, we have the critical value of J. On the graph, which is named a Doniak phase diagram, the point with a temperature of 0 Kelvin and the critical J value is called a quantum critical point, or a QCP. QCPs are great for investigating all sorts of strange phenomena, because while thermal fluctuations are greatly reduced, if not entirely absent, quantum fluctuations limited only by the Heisenberg uncertainty principle can introduce a large amount of disorder, or entropy. Therefore, unique phases are created in which this entropy increase is balanced. Experimenting with materials around a QCP can be as simple as using pressure to locate the critical value of J, and we often find interesting properties like superconductivity. Conventional superconductivity is theorized to operate using ideas such as Cooper pairs, but adding in magnetic impurities destroys the long-range interactions pinning these ideas together. However, around QCPs, superconducting heavy fermion materials have been observed. But, I hear you say, I thought the defining characteristic of a heavy fermion material was its resistance-temperature relationship. If it has zero resistance, how can you even tell if it's still in that heavy fermion state? The answer is to look at other properties affected by electron mass. See, one of these properties is heat capacity, or the amount of energy a material needs to increase in temperature by a given number of degrees. Since temperature is, in many senses, a kinetic energy, it should follow that heavier particles will require more energy to increase in temperature. And in heavy fermion materials, we see just that. The electron component of the material's heat capacity increases. And so while, in a superconducting phase, it would be difficult to identify a heavy fermion material by its resistance, we can instead look at the material's heat capacity. And yeah, heavy fermion superconductors are definitely a thing. This has led to new theories being developed to explain how coupling between electrons can form, despite the magnetic impurities, to produce a model similar to the Cooper pair model. To be clear, this is actually the primary use of heavy fermion materials. Just like superconductors, their unique properties only come into effect at extremely low temperatures, meaning the costs of maintaining those effects in a commercial product are prohibitively high. But by investigating these materials in a controlled setting, we can obtain data on some of our most fundamental ideas. These materials can give us unique insights, developing ideas such as fermion interactions, or quantum criticality, the principle which allows the heavy fermion superconductor phase to exist. The reasoning I gave earlier, that new phases were formed to offset the entropy shift of quantum fluctuations, was deliberately vague, because there's not a clear consensus of how this actually works. It's still being researched. Whether any of it will turn out to have a practical use is yet to be seen, but regardless, going forward, heavy fermion materials will play a large role, not only in developing our understanding of fermion interactions, but perhaps even in testing theories originating in other areas of research entirely. So, to recap, electrons in a metal can be modelled as a Fermi liquid, as if they don't actually interact with each other, but have some other difference in one of their fundamental properties. By introducing magnetic impurities into a metal, it can appear as though the electrons become heavier. And this can lead to all sorts of interesting properties, notably quantum criticality and the counterintuitive heavy fermion superconductivity. And really, we don't know that much yet. There's still a lot of work to be done. Thanks for listening, everyone.